Hi, my name is Peter Yakovlev. I'm a data scientist and science communicator at Kairos Aerospace. At Kairos, we use proprietary airborne survey technology to find methane emissions in oil and gas fields. In the last year alone, we've helped our customers eliminate methane emissions equivalent to taking 4.6 million cars off the road. Today, I'll be discussing how we can determine the best technology and operating practices to find and eliminate the majority of methane emissions in an oil and gas field. I'll start off with some acknowledgments. This talk relies heavily on work done at Stanford University by Evan Sherwin and Yuli Chen and Adam Brandt's group at Stanford. The modeling portion of this talk was done in collaboration with Highwood Emissions Management. So why focus on methane? The answer is simple. As of 2017, the amount of methane we're emitting will produce as much global temperature change as all of the CO2 we're emitting. But because methane we release into the atmosphere can break down in as little as 80 years, compared to over a century for CO2, eliminating methane emissions can quickly reduce the speed of global warming. So if we fix methane, and fix it fast, we can fight warming in the short term and give us more time to avert climate catastrophe. So how can we reduce methane emissions? One tactic is to focus on the oil and gas industry, which accounts for about a third of methane emissions in the United States. The majority of these emissions are caused by large and unplanned methane leaks. Let's go over a common scenario. Something breaks in an oil and gas field, say a valve or a seal. You could get a massive leak like the one shown at right, leaking 915 kilograms an hour of methane, or the CO2 equivalent of roughly 2,500 cars driving on the interstate. Compared to other sources of methane, same for agriculture, a discrete leak like this can be stopped and fixed fairly easily. But there's still a challenge. You need to know it's there. Methane leaks are hard to find because they are odorless, invisible, and can be distributed across large oil and gas operations that cover hundreds of square miles and thousands of pieces of equipment. Now, the good news is that there are both regulatory and industry initiatives to tackle methane emissions, as well as a consensus on the need to find and fix methane leaks. So the large part of the challenge is therefore technical. So how do we effectively find and fix these leaks across all of the oil and gas basins across the United States and the world? In today's talk, I will answer this question and provide some routes forward to finding scalable solutions to mitigating methane emissions in the oil and gas industry. Right now, there are two broad approaches to finding and fixing leaks in an oil and gas field. The first is a regulatory industry standard where an oil and gas operator scans every piece of equipment with a handheld optical gas imaging camera. This approach has one major advantage. It is highly sensitive and can detect very small leaks. However, there are some drawbacks to this approach. The sensitivity of OGI varies considerably based on the operator experience, and there are some leak types, such as unlit flares, that can emit a ton of methane but not be detectable by OGI. And because this is a ground-based approach, it is not easily scalable across basins. No matter what, you need to send someone to each site, which is slow and costly. An alternative is a tiered approach. This uses a suite of technologies at different scales, such as OGI paired with an airborne survey, to quickly find and eliminate the majority of methane emissions. Each technology has its own sensitivity and potentially frequency of surveys. The advantage here is that you combine the strengths of each approach. In this case, you have rapid, large-scale surveys to find big leaks quickly, and slower but more sensitive ground surveys to find all of the smaller leaks. But this all sounds good in theory. How does it compare to the standard method? How will it translate to the field? We need to actually quantify the effectiveness of this alternative tiered approach to show that it is equally effective. The fact is, in order to understand how a technology performs in the field, you need to know what methane emissions actually look like. And there has been a concentrated effort to do so over the last decade. Before airborne technologies were available, ground-based surveys were the only option. Field studies, logistically, could only visit a small number of sites and would very carefully survey each component. And they found a lot of small leaks. These observations were then extrapolated to the full field and led to the determination that technologies need to be highly sensitive in order to find and eliminate the majority of emissions. But it turns out that this conclusion was not quite right. More recent aerial surveys by Kairos, Stanford, and JPL have been able to cover vastly more ground, covering tens of thousands of sites as opposed to the hundreds of sites surveyed in previous studies. And although these survey technologies could not detect the very smallest leaks, they found significantly more methane emissions, in some cases over 20 times more, than expected from previous studies. Why was that? Well, airborne surveys found that at about 1 to 3% of sites, large super emitters were generating the vast majority of emissions for a basin. These large super emitters were absent from the previous literature because they were so rare across the landscape that from a purely probabilistic perspective, there was very little chance they would be observed by a small-scale study of only a few hundred sites. This discovery unlocked an opportunity. By rapidly surveying large basins, you could find and fix most of the emissions. But it also means that if we are going to quantify the effects of our tiered technology approach, we need to construct an emissions distribution that describes both small emissions as well as very large, but very rare, super emitters. So that's what we did. We focused on the Permian Basin, which is responsible for most of the oil production in the United States, in order to understand its true methane emissions. We carried out a large aerial survey that included 90% of the wells in the New Mexico portion of the Permian Basin. The study found 958 emissions at about 117,000 sites. Fewer than 1% of sites had an emission, reiterating the need for large surveys to get a good picture of what's going on. 50% of these leaks came from the tail of the distribution and have emissions greater than 308 kilograms per hour. In other words, big leaks really matter, but we still need to incorporate emissions that are smaller than what we can detect with our sensor to have a full picture of emissions in the Permian Basin. We do so by incorporating emissions generated by a bottom-up inventory-based model from a recent study by Rutherford et al. We then stitch the modeled and measured datasets together in order to create an emissions rate distribution, shown at right. This distribution shows the probability that leaks of different size occur. Do note that the x-axis is logarithmic, so we go from the tiniest leaks of a few grams per hour to extremely large leaks of several thousand kilograms per hour. So what do our results show? 50% of emissions come from leaks greater than 224 kilograms per hour. In other words, very large leaks make up half of the total emissions in the Permian Basin. Additionally, our aerial survey is able to find 83% of all emissions in the Permian Basin. These two data points indicate that you really don't need a sensitive instrument to find the majority of methane emissions. But is this distribution true for other oil and gas basins? If we're trying to evaluate the effectiveness of tiered multi-technology emission surveys, we want to make sure that these approaches work in more than just one place. The answer is we don't yet know what the emissions distributions look like in other oil and gas basins, but it's an active area of research. In the meantime, we have to use other sources of data to evaluate the effectiveness of tiered surveys. In this case, we decided to pair our constructed Permian distribution with a more conservative estimate generated from observations by O'Mara et al. In 2018. This study has 1,009 ground-based emission samples, mainly from vehicle-based mobile labs, and you can see that the dataset is very different from our Permian emissions distribution. It has many fewer super emitters, which we expect from a ground-based survey, and it also incorporates multiple basins with a key exclusion of the Permian. So let's consider these distributions as n-members. Some basins may have large emissions, like the Permian. Others may have mainly small emissions, like our rest of the US distribution based on O'Mara. We have our distributions, and now we need to test and evaluate the performance of tiered survey approaches for both. For that, we used a numerical model. There are a few leak detection and repair models out there. We used LDARSim, a peer-reviewed, open-source, agent-based numerical modeling framework. LDARSim generates emissions based on an input emissions distribution, and then models the detection and repair of those emissions, or lack thereof, based on different applied technologies. It allows direct comparison between different technologies and survey approaches, including both the sensitivity and frequency of surveys, as well as how long they take to carry out. We decided to vary these parameters in a few different ways. Here's an outline of our different tests. We tried a few different survey strategies. One, an OGI-only approach using quarterly OGI surveys, or the standard way of doing things that we compare the results to. Airborne surveys only, with some follow-up for detections with OGI, as well as a tiered approach that incorporated both airborne surveys and additional OGI surveys. We also varied the sensitivity of these airborne surveys from 10 to 40 kilograms an hour, as well as changed their frequency from 4 to 6 times per year. Let's walk through our results. On the x-axis, we showed the sensitivity of the airborne technology used in each test. On the y-axis, we showed the total percent of mitigated emissions achieved by that program. For today, let's focus only on the relative performance of each program rather than the actual performance on the y-axis. The white dashed line shows the performance of quarterly OGI, that standard way of doing emission surveys. The red and blue lines represent different sets of model runs. Where they fall above the white dashed line is where the modeled method outperforms the standard method. Here I'm showing results for both of our distributions. The pair of red lines are from our Permian distribution, and the pair of blue lines are from our rest of US distribution from the OMARA data. Each distribution that has one line showing model results with and without an additional OGI survey. In other words, an aerial only and a tiered approach. We can use this chart to estimate the instrument sensitivity needed to achieve equivalence to quarterly OGI. When using our Permian distribution, all sensitivities perform better than OGI. You can see that because the red line never crosses the white line. If I were to extend the x-axis, that crossover would happen around 100 kilograms per hour. That is because the Permian is dominated by super-emitters, which aerial surveys excel at finding quickly. For the rest of the US distribution, the one with mainly smaller emissions, a sensor with a sensitivity of 27 kilograms per hour and an annual OGI inspection, or one with a sensitivity of 19 kilograms per hour and no annual OGI inspection, can achieve equivalency to quarterly OGI. We can then adjust the frequency of the airborne surveys in our model and see what happens to our assessment of equivalency. When our airborne survey is carried out one fewer times each year, you can see the lines shift to the left. We now need a slightly more sensitive technology, although not in the Permian, which is still much better for any airborne approach. And reducing our number of surveys down to quarterly, we see the same shift. So here's a quick high-level summary of the conclusions from these results. For the Permian, all tested aerial sensor sensitivities and survey frequencies perform better than quarterly OGI. For the rest of the United States, a variety of sensor sensitivities and survey frequencies can match quarterly OGI. Tiered approaches generally perform better than single sensor approaches. But we need to know the emissions distributions in order to properly develop LDAR programs and optimize emission mitigation strategies. So overall, we see that tiered approaches work, but they must consider both sensitivity and frequency. So how do we translate this into recommendations for mitigating emissions using a tiered approach? Our answer is a matrix. We take a more conservative approach and lean closer to the rest of the United States distribution, on the off chance that the Permian Basin is not representative of the rest of the United States. For a tiered approach, our results show that aerial surveys need to have a sensitivity of around 30 to 40 kilograms per hour, with more frequent surveys allowing for a less sensitive instrument. If we wanted to do an airborne-only approach, aerial surveys need to have a higher sensitivity of somewhere around 15 to 25 kilograms per hour. So in conclusion, tiered survey approaches using multiple technologies can reduce methane emissions as well or even better than the industry standard quarterly OGI inspections. However, in order to properly evaluate methane reduction strategies, you need to incorporate super-emitters. For that, basin scale surveys are the best way to quantify real-world emissions. Thank you.